Welcome to activity 3.2. This is part 2 on how to draw a free body diagram. So by the time you get to here, you should have already been done with activity 3.2 through question 7. But question 8 has you drawing a free body diagram. And so this is an introduction to free body diagrams, or if you want to review, you can come back and watch this video. So free body diagrams. This is a new one, and you've already created force models. But this is it's using a force model, but it's looking at it a little bit differently. So this is new, and you need to do these practices in the notes section of your book and use these as a reference. So remember, this is an interaction table. So if we were to create this interaction table, and remember when we create an interaction table, all we're doing is we're going through here and we're filling out a plus if they interact or a minus sign if they do not interact. So let's fill one out together. So construct an interaction table on a force model that represents a drop ball. So let's say this represents a ball that's about to be dropped. It hasn't been dropped yet. And the reason I know that is there's a hand. Once it's been dropped, you probably don't need the hand in it at all. So the hand and the ball, would there be an interaction? If it hasn't been dropped yet, yes, there would be. How about the hand and the earth? Yep, always. The earth and the ball, yes. So now when I go down here, the earth and the ball is a plus. How about the earth and the hand? Yep, we saw that over here. And how about the ball and the hand? Yep. So what I have to do now is if I were to create a model, my model would show that there would be arrows between all these. And when I draw those arrows, remember, if it is a force that acts at a distance, it would be a dashed line. So I could create something like this. And you can go ahead and pause the video and see if you can make this on your own. You know, I might have the hand here, or I'm sorry, the hand was above, here's the ball, and maybe I would have another rectangle. Now, you might be saying, does this have to touch? It doesn't have to, because if I draw dashed lines, that represented acts at a distance, so there is no contact. So I could have drawn this rectangle way down here. In fact, I think the answer key does. But there would also have to be solid lines here, because these show forces that are contact forces. So if I were to go ahead and if I were to look at the key, here it is. See, here they didn't touch it. You could touch it. You just have to make sure there's dashed lines. You can see I forgot a line. So I didn't draw on any dashed lines from the hand to the earth. So I've got to make sure I have all those in here, and this is what it would look like. Now, if we were to draw another model after being dropped, we could take out the hand, and this is what it would look like. So what are we doing differently then? Because you've learned how to do all this. What is a free body diagram? Now, this new model, this free body diagram, will only show the tennis ball and the forces it is subjected to. So right now, if for number 2 you had to draw an interaction table and a model. So when you guys are pushing on a tennis ball from both sides and you drew in the force model, you would show arrows going from the hand to the ball and from the ball to the hand, or hand 1, from the ball to the hand, and from the hand to the ball for ball 2. But not all forces cause movement. And so we're going to look at a model of a single object, and we're going to look at the forces that act on it. And these are called a free body diagram when you look at this type of model, because we're freeing it of all the surrounding forces that are being applied, or that it is applying to other things. So the influence of all the surroundings is represented through the forces they apply to the object of interest, not the forces the object applies to everything else. So if the force applied by hand 1 is greater than the force applied by hand 2, this is how we got the ball to move. And we can actually start drawing larger lines. Do you notice how this line is larger than this line here? This would represent that force 1 was larger than force 2. So that means the ball should move in that direction. So as we start to draw models, we want to start to make sure that we're drawing lines equal if they truly are equal, and if they're not equal, make sure they're not drawn equally. So what happens if the force applied by hand 2 is greater? Well, then look here. The arrow is the other way. And so the ball would be moving in that direction. So it would begin moving and it would move in that direction. So what does a free body diagram do? And when we look at what's, well, first of all, let's look at what's happening in this diagram. Is there going to be any movement? How do we know? Well, if these two are equal, there should be no motion because the forces are equal. So explain what is happening in each diagram. Well, if we look at this, there should be no motion because the pull on gravity is the same as the pull on the hand. However, if the hand is greater than the pull of gravity, well, the ball should be moving up. So we can start to look at force models and start to figure out how things move. And that's what a free body diagram, it starts to look at how things are moving, why they're moving. And you should be able to look at a free body diagram and figure all this out. So in which direction does the ball begin to fall when it's dropped? Well, obviously it begins to fall down. In which direction does the ball begin to move when it's held in your hand? Well, it doesn't move at all if the forces are applied equally. Or if your hand is applying more force to the ball, it actually might be moving up. So you have to, it's a tough question to answer unless you know how much force the hand is applying to things. So what happens if instead of holding or pulling the ball up, your hand pushes it down? Well, the ball will begin to move down even more rapidly. So if you just release the ball from your hand, it's going to drop. But if you release it and then you push it down, it's going to go a lot faster. In other words, the force that you're applying to your hand is reinforcing the pull of gravity already. So forces that are applied to an object in the same direction reinforce one another. So think about the activity we did with the basketball and the tennis ball. And if you remember, we dropped one and we watched the tennis ball launch up into the air. Now, if we want to lift a heavy box, ask someone to help, because if you can't pull up on the box and you can't lift it up, having someone else help you, they're reinforcing your force that you're applying to the box. And it's going to make it a little bit easier to move up. So now we get back to drawing a free body diagram of a held ball, or ball that's held in your hand before it's dropped. And what we're going to do here is we're only going to take a look at the forces that are being applied to it. We're not going to be concerned, oops, sorry about that, let me grab a marker. We're not going to be concerned about the forces that the ball is applying to other things, because those forces do not affect its motion. So we have gravity pulling it down. Now if it's being held in your hand, I'm going to do my best to make these arrows approximately equal. So your hand is pulling up on the ball and gravity is pulling down. This is all I would need for a free body diagram. In fact, here's the answer key. Now, you might be saying, Mr. Rattoon, what about the other, you didn't draw on the other forces. What about, the hand is touching the ball and the ball is actually pulling up on the earth? Well, we don't want those in this. This is a free body diagram. Those forces do not affect its motion. The fact that the ball is pulling up on the earth does not affect its motion. Now, the earth pulling down on the ball affects its motion. And the ball being pulled up by the hand affects the motion, but the motion of the ball is not impacted by it pulling down on the hand. So we're freeing it of all outside forces. We're only going to take a look at the forces being applied to an object. So what would a free body diagram of ball look like after being dropped? Well, here was before, here would be afterwards, because now the hand's not touching it anymore, so we don't have to put that in there at all. You might be saying, well, what about gravity? If we backed up, you might be saying, what about gravity on the hand? Gravity on the hand does not impact the ball at all. Gravity on the ball impacts the direction of the motion, but the gravity on the hand, so if we backed up to the force model, that would have it in there. It would have earth and would have dashed lines going up to the hand. But in a free body diagram, it's freed of all those outside influences. So, in a nutshell, that's how to create a free body diagram. You're only looking at the forces that are being applied to it. that affect its motion. You're freeing it out of all other forces. So go ahead and complete the conclusion questions on page 29. And then there's one scientific principle that you can add. An object's motion is influenced only by the forces that are applied to it, not by the forces it applies to others. So that's basically a free body diagram. So again, it's very, very important that if you have questions, we can do some examples of this, but make sure you ask on how to draw a free body diagram. So if it's on the test, you know how to do it.